Two batteries, same size, the same charge stored inside. One is lithium, the chemistry already in your phone. The other is sodium, built from salt with no lithium, no cobalt, no nickel anywhere in it. They look identical, but push them and they fight back in surprisingly different ways. And one quick electrical test can reveal how. No teardown, no microscope. Let's run it on real physics models and let the two curves tell the real story. The test is called impedance spectroscopy, and the idea is gentle. Instead of forcing the battery, we tickle it. We send in a tiny wiggling current, first fast, then slower still, across a whole range of rhythms, and we watch how hard the battery pushes back at each one. Fast wiggles only feel the surface. Slow wiggles reach deep inside. Plot the answer the right way and you get this shape, the Nyquist plot. Plain resistance runs across the bottom. The springy storing part runs up the side, and you read it left to right like a sentence. The left foot is the ohmic resistance, mostly the electrolyte and the contacts. We call it R0. The arc in the middle is how reluctantly the chemistry reacts, the charge transfer. And the long tail at the end is ions slowly crawling deep inside, diffusion. 3 features, 1 curve. Hold that picture. Now meet our two contenders, and these are not toys. They are peer-reviewed physics models, the very same ones researchers publish with. Sodium is the Chayambuka 2022 model, a hard carbon electrode against an NVPF electrode, published in electrochemical acta. Lithium is the Chen 2020 model, graphite and silicon against nickel-rich NMC, the famous LG cell, from the Journal of the Electrochemical Society. Both are full Doyle-Fuller-Newman models. They solve the real diffusion and reaction equations through every single layer of the electrode. But here is the catch, and it matters. The sodium cell is a tiny 3 mAh coin cell. The lithium one is a 5 Ah powerhouse. Comparing their raw impedance would be like racing an ant against an elephant. So we do the fair thing. We hold every internal property fixed, the thicknesses, the particle sizes, the chemistry, and we stretch only the electrode area until both store exactly the same charge. Then we report impedance per square centimeter. Same capacity, same conditions, true apples to apples. Now we run it for real. Inside, the solver takes each model, linearizes the full physics around a half-charged resting point, and solves it at 60 frequencies, from 10,000 wiggles a second all the way down to 1 every 50 seconds. This is real computation, not a cartoon. Watch lithium first. The curve starts at its ohmic resistance, sweeps up into a tidy little semicircle as the chemistry kicks in, then tips into a short diffusion tail. Clean, compact. Now sodium, same start, and then the arc just keeps going. It balloons outward, far wider than lithium, before its own tail finally lifts away. Here they are together, on one axis, and the very first surprise is right at the start. Look at where each curve touches down on the left, the ohmic resistance. Sodium is actually lower than lithium, about 9/10 of an ohm centimeter squared against nearly 3. The bigger ion, less resistance? Yes, because sodium holds its solvent shell more loosely, so the electrolyte around it actually conducts a little better. But now follow the arcs. Lithium's charge transfer loop is small, around 12. Sodium swells past 300. In this pair of models, sodium's chemistry is far more sluggish at the surface and slower to diffuse within. So sodium wins on ohmic resistance and lithium wins on the reaction. No clean knockout, a split decision. To put real numbers on it, we fit an equivalent circuit, a Randall's model. A resistor for the ohmic part, a resistor and capacitor pair for each reaction arc, and a Warburg element for diffusion. It pulls each resistance out cleanly, but a squashed arc can hide several overlapping processes at once, so we do one more trick. We transform the curve into a distribution of relaxation times. Instead of one blurry arc, we get separate peaks, each at its own timescale. The surface film, the charge transfer, the diffusion, split apart and labeled. And here is the honest footnote. That sodium model is a 2021 laboratory cell, early hard carbon, and its surface film is less stable too, because sodium's SEI dissolves more easily, which is exactly why engineers add a pinch of FeC to seal it. Today's commercial sodium cells have already closed almost all of this gap. So who actually wins? The grown-up answer is nobody universally. Sodium is genuinely easier at the interface in principle. Shedding its solvent shell costs less energy than lithium's, 148 against 208 kilojoules per mole. Its real weaknesses, diffusion and film stability, depend entirely on the host material, and in open framework host sodium can even diffuse faster. In today's best commercial cells, total resistance is essentially tied, around 16 milliohms each. Where sodium clearly wins is the cold, over 20% more power at -30 degrees, and cost, no lithium, cobalt or nickel, and safety, it can even ship completely empty. Lithium still wins on energy density. Different tools for different jobs. So next time you meet a Nyquist curve, read it like a sentence. The left foot is the ohmic resistance, the arc is the reaction, the tail is diffusion. Sodium is not the loser the old textbooks imply. It is simply a different trade. Next time, we cool both cells to -30 and watch the arcs explode. Subscribe, and I will see you there.